Hi students, welcome to my channel. So now in this video, I would like to discuss about optical system design. So when you are going to design any optical fiber communication system, you must consider different losses, dispersions, and non-linearity of the fiber. And we have some requirements for system design. So when you see the requirements, so the first one is type of transmission you are preferring. So type of transmission means you may prefer for analog communication, analog transmission. If you want to transmit a TV signal, it should be an analog signal, analog transmission, and it requires a small bandwidth and better linearity. And whenever you want to transmit a sampled voice, then you must go for digital transmission. And the next one is system fidelity. So system fidelity is simply defined as the correctness of the data which is received at the receiver side. And this can be expressed as bit error rate, BER. So generally, bit error rate is expressed as a number of bits in error divided by total number of bits transmit. So this is simple expression, bit error rate is defined. Okay. And the next one is spacing between terminal equipment or repeaters, number of repeaters or intermediate repeaters, how many you are using, and bandwidth required for transmission, and reliability. So reliability means the system should be able to adapt new technology and new data rates. And the cost. So cost is also be considered because it is very important while designing any system. So generally, when you take the cost effectiveness, you must consider installation cost, components cost. All these are to be considered. Okay. So next, digital links. So we are going to use point-to-point links. So here, whenever you take a small block diagram for point-to-point links, it is going to be information source and it is connected to optical transmitter. And at the receiver side, you are having optical receiver and the user, the final destination. In between the two, you have optical fiber, which is connecting our transmitter and receiver. This is generalized block diagram for point-to-point communication or point-to-point link. So here, the system requirements to analyze optical fiber links are the desired transmission distance, how much distance you want to align for optical fiber, and the data rate or channel bandwidth, and bit error rate. Bit error rate already just now I told you. Okay, so these are the three parameters or three requirements to be considered to analyze the transmission link. Okay, and among these requirements, we need to consider about components and their characteristics. So here, based on the type, we are going to have different characteristics. So if you take multi-mode or single mode fibers, then you need to consider about core size, core refractive index profile, bandwidth or dispersion, attenuation, and numerical aperture or modified diameter or simply spot size. And whenever you take LED or laser diode optical source, based on optical source, you must consider emission wavelength, spectral line width, optical power, effective radiating area, emission pattern, number of emitting diodes. And at the receiver side, when you consider pin diode, or avalanche photodiode, you must consider responsivity, operating wavelength, speed, and sensitivity. All these parameters already discussed in the previous units. And the other thing is component choice. So we have different parameters here. So when you take optical fiber type or parameters, you may have multi-mode or single mode fiber. While designing optical system design, what are different components you need to take? So whenever you take optical fiber type or parameters to be considered, so you may have multi-mode fibers or single mode fiber. And again, in the multi-mode or single mode fiber, you need to consider core size, refractive index profile, attenuation, dispersion, mode coupling, strength, jointing, like that. And coming to source type, when you want to take one optical source, then you have laser diode and LED, which is better one you need to consider, and optical power launched into the optical fiber, and what is the rise time and what is the fall time and stability. Okay, and the next one, transmitter configuration. So design for digital analog transmission input, and the other one is detector type characteristics. What are detectors we have, and how to select a detector, and what are different parameters we have. That is responsivity, response time, and active diameter, bias voltage, dark current, all these things. And receiver configuration. So what type of receiver configuration you need to pre-amplify design, So it must be low or high impedance, transimpedance, front end, and signal to noise ratio, dynamic range. All these parameters you need to consider. And when you go for modulation and coding, so you must consider source intensity modulation, pulse modulation techniques like pulse code modulation, and we have different amplitude techniques. We have amplitude shift keying, phase shift keying, frequency shift keying, like that you can use, and adapt to delta modulation. So among all these types, you must consider based on your system requirement. And what are system considerations? So basically, system considerations are taking based on operating wavelength, photodetector, optical source, and optical fiber. So when you go for optical photodetector, when you go for optical operating wavelength, so operating wavelength completely depends on transmission distance and attenuation. So this operating wavelength depends on transmission distance and attenuation. So operating wavelength always depends on the two. For long distance communication, generally O band, U band regions are preferred because at these two bands is possible and dispersion is also very for long distance communication only. For short distance communication, you must prefer 770 nanometers to 910 nanometers wavelength. In this region, you can prefer for short distance communication. So this is the operating wavelength. And coming to photodetector. To select a photodetector, you must consider minimum optical power that must fall on the photodetector to satisfy bit error rate and designing cost, circuit complexity, bias voltage. And coming to optical source, you must consider data rate, transmission distance, cost, and signal. So these are the factors you must consider. And when you go for optical fiber, the very important parameter is numerical aperture. You must consider numerical aperture and attenuation characteristics. Attenuation characteristics. These are the system considerations you must follow. And next, how to evaluate the system performance after designing an optical communication system. The performance can be analyzed. So in order to analyze the system performance, we have two methods. One is link power budget, and second one is rise time budget. Link power budget and rise time budget. Link power budget analysis determines the power margin between optical transmitter and the receiver, and rise time budget determines the dispersion limitation of optical fiber link. Dispersion limitation of the optical fiber link. And coming to link power budget, this is very important. So here, this is simple optical power loss model where we have transmitter side and receiver side, and the transmitter and receiver are connected with optical fiber, and in that optical channel we have filters and connectors and splices. Okay, different components are used. And here, when you take this link power budget, majorly link power budget analysis is simple method to determine the power margin. So it can use power margin between optical transmitter, and that is optical transmitter output, and minimum receiver sensitivity. And whenever I'm assuming that P in is the input power and P out is the output power. So here the loss is taken as 10 log P out by P in. So this is the loss which is going to be. So here the optical power received at the optical or photodetector depends on the amount of light coupled into the fiber, and the losses occur in the fiber and at the connectors and splices. And here the loss is taken between input power and output power at the same time the amount of loss considered at different components in this channel, different components included in this channel, like you take splices or connectors, all the things you can. So now, if I'm taking P in is the input power and P out is the output power, P out is the output power for each component. So for each component, the loss is expected. If P in is the input power and P out is the output power for the component, then this is equal to 10 log P out output power. Okay, and generally this power, the link margin is about 6 to 8 dB, 6 to 8 dB, and from the system, the total power loss PT is equal to, it is expressed as PS minus PR, PS minus PR, where PS is the transmitted power and PR is the received power, receiver sensitivity. And this is also expressed as NC, LC, I will tell you, plus NSP, LSP, plus alpha FL plus PSM. So here N represents, NC represents the number of components, number of connectors used in the link, and LC is the loss occurred at each connector, and SP is the number of splices used in the link and loss at each slice, and alpha F is the fiber attenuation in decibels per kilometer, and PSM is the system margin, SM for system margin. Okay, and for this is